Richard Feynman once said something that should terrify you. He said, "I think I can safely say that nobody understands quantum mechanics." And this wasn't some random person. This was Richard Feynman, Nobel Prize winner, one of the greatest physicists who ever lived, the man who helped build the atomic bomb, the man who could calculate things in his head that other scientists needed computers for. And he's telling you that nobody, not even him, truly understands the fundamental nature of reality. Let that sink in for a moment. The smartest people on the planet, the ones who built your phone, who send rockets to Mars, who can predict eclipses thousands of years in advance, they don't actually understand what reality is made of. They can use it. They can manipulate it. They can make incredibly accurate predictions. But understand it? No. And here's what makes it worse. The more you learn about what Feynman discovered, the more you realize he's right. Reality doesn't just fail to make sense. Reality actively contradicts everything your brain thinks it knows about how the world works. Let me show you what I mean. Let's start with something simple, something you've known since you were a child. Things are made of stuff, solid stuff. Your desk is solid. The ground beneath you is solid. You are solid, right? That's obvious. That's fundamental. You can touch it. You can feel it. Except, according to Feynman and quantum mechanics, that's completely wrong. You are not solid. Not even close. Here's what you actually are. You're mostly empty space. Not metaphorically, literally. If an atom were the size of a football stadium, the nucleus would be a tiny marble in the center, and the electrons, they'd be smaller than grains of sand, buzzing around somewhere in the outer seats. Everything in between? Nothing. Empty. Void. So when you touch a table, you're not actually touching anything. The electrons in your hand are repelling the electrons in the table. It's electromagnetic force, but there's no contact, no actual touching. Just forces pushing against each other across empty space. You have never touched anything in your entire life. Think about that. Every hug, every handshake, every time you've held something, you were hovering just above it, suspended by invisible forces. But it gets stranger. Much stranger. Feynman didn't just tell us that atoms are mostly empty. He told us something that breaks your brain. He said that particles, the fundamental pieces of reality, aren't really particles at all. They're not little balls. They're not tiny marbles. They're not objects in the way you understand objects. Here's what Feynman discovered. Electrons, photons, quarks, all the fundamental particles, they exist in what's called a superposition. That means they're in multiple states at once, multiple places at once. They don't have a definite position until you measure them. Before you look, before you interact with them, they're spread out. They're a cloud of probability. They're everywhere they could possibly be, all at the same time. Does that sound insane? Good, because it is insane. It violates everything you think you know about how objects work. An object is in one place. That's what makes it an object. But at the quantum level, particles aren't in one place. They're in all possible places simultaneously. And the moment you try to look, the moment you try to measure where it is, the superposition collapses. The particle picks a location. But before you looked, it wasn't anywhere specific. It was everywhere. Now, you might think this is just theoretical, just math, just some abstract idea that doesn't affect the real world. But Feynman showed us that this is the real world. This is how reality actually works. And he proved it with one of the most famous experiments in physics, the double slit experiment. Let me walk you through it, because once you understand this, nothing feels solid anymore. Here's the setup. You have a barrier with two slits in it. You fire particles, let's say electrons, at the barrier. Some go through the left slit, Some go through the right slit. Behind the barrier, you have a screen that detects where the particles hit. Simple, right? If particles are little balls, you'd expect two bands on the screen, one behind each slit. That's what common sense says. That's what your intuition demands. But that's not what happens. Instead, you get an interference pattern, multiple bands, light and dark stripes, the kind of pattern you only get from waves. When two waves overlap, they interfere with each other. Where the peaks align, you get bright spots. Where a peak meets a trough, they cancel out. Dark spots. This is what water waves do. This is what sound waves do. But particles aren't waves. Or are they? Here's where it gets disturbing. If you fire the electrons one at a time, if you send them through the slits individually, with long gaps between them, you still get the interference pattern, one electron at a time, each electron going through the slits alone. And somehow, it interferes with itself. It acts like it went through both slits simultaneously. Think about what that means. A single particle, one electron, exists in a superposition of going through the left slit and going through the right slit at the same time. It takes both paths. It interferes with itself. The electron isn't in one place. It's in multiple places. But wait, what if you try to catch it? What if you put a detector at the slits to see which one the electron actually goes through? Then everything changes. The moment you measure which slit the electron passes through, the interference pattern disappears. You get two bands. The particle behavior. The electron stops acting like a wave and starts acting like a particle, just because you looked at it. Feynman called this the central mystery of quantum mechanics. The act of observation changes reality, not because your eyes have magical powers, but because measurement, any kind of interaction, collapses the superposition. Before you measure, the electron is in both places. After you measure, it's in one place. And there's no way around this. It's not a limitation of our technology. It's not something we'll solve with better instruments. This is how reality works. Particles exist in superposition until they're observed. Then they collapse into definite states, and nobody knows why. Here's what Feynman said about this. He said, if you think you understand quantum mechanics, you don't understand quantum mechanics. Because the moment you think it makes sense, you've fooled yourself. You've created a mental model that feels comfortable, but that model is wrong. Reality doesn't work the way your brain wants it to work. Now let me show you something even stranger, something that bothered Feynman so much he spent years thinking about it. It's called quantum entanglement, and Einstein hated it. He called it spooky action at a distance. Here's how it works. You can create two particles that are entangled, connected, linked at a quantum level. When you measure one particle, let's say you measure its spin and find it spinning up, the other particle instantly has the opposite spin, spinning down instantly, no matter how far apart they are. You could separate these particles by billions of miles, put one on Earth and one on the other side of the galaxy, and the moment you measure one, the other responds, faster than light. Actually, not faster than light, because no information is being sent, but the correlation is instant. Measure one, know the other. Always. Every time. Without fail. Einstein thought this proved quantum mechanics was incomplete. He thought there must be hidden variables, secret information that determines the outcome in advance. But Feynman and others showed that Einstein was wrong. There are no hidden variables. The particles genuinely don't have definite states until you measure them. And when you measure one, the other instantly takes the opposite state. Not because they're communicating, not because information travels between them, but because they're part of the same quantum system. They're entangled. They're not really two separate particles. They're one system spread across space. Does this make sense? No. Did Feynman understand it? He said he didn't, but he could calculate it. He could predict it. He could use it, and that's what mattered. Feynman had a philosophy. He said, "Shut up and calculate." Don't worry about what it means. Don't worry about why reality is this way. Just figure out the math, make predictions, test them. If the predictions work, the theory is good. And quantum mechanics works. It works better than any theory in the history of science. The predictions match experiments to 10 decimal places. 10. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. But here's the thing Feynman also said. Just because the math works doesn't mean you understand it. You can use quantum mechanics without understanding what it means. And that's what physicists do. They calculate, they predict, they build technology, computers, lasers, MRI machines, GPS satellites. All of this works because of quantum mechanics. But ask a physicist what an electron really is, and they'll give you equations, not an explanation, not a picture, just math. Because there is no picture, there is no way to visualize what's actually happening. Your brain can't do it. Evolution didn't prepare you for this. You evolved to throw rocks and avoid predators. You didn't evolve to understand superposition. So your intuition fails completely. And that's okay. Feynman said, nature doesn't care what you find easy to understand. Nature is what it is. Now, let's talk about something that makes this even worse. Let's talk about the uncertainty principle. Feynman loved the uncertainty principle because it's so simple and so devastating. Here's what it says. You cannot know both the position and the momentum of a particle at the same time. Not because your instruments aren't good enough, not because you're clumsy, but because the particle doesn't have a definite position and momentum at the same time. This isn't a measurement problem. This is reality. If you measure the position of an electron very precisely, you lose information about its momentum. If you measure its momentum very precisely, you lose information about its position. The more you know about one, the less you can know about the other. It's a trade-off built into the fabric of the universe. Why? Nobody knows. Feynman didn't know. He could calculate it. He could derive it from the math. But what does it mean? What does it tell us about the nature of reality? He didn't have an answer. And here's what's disturbing. This uncertainty isn't just about electrons. It's about everything. Energy and time have the same relationship. The more precisely you know the energy of a system, the less precisely you can know when it has that energy. This has consequences. Real, measurable consequences. For instance, particles can pop into existence out of nothing. Vacuum isn't empty. It's seething with virtual particles. Particle-antiparticle pairs appearing and disappearing constantly. Borrowing energy from the vacuum, existing for a tiny fraction of a second, then annihilating. This isn't speculation. We've measured it. The Casimir effect. Two metal plates placed very close together in a vacuum experience a tiny force pushing them together. Why? Because the vacuum between them has fewer virtual particles than the vacuum outside. The universe is pushing on the plates. Empty space has energy. Empty space does things. Nothing is actually nothing. Does this make sense? No. Did Feynman understand why vacuum energy exists? He understood the math. He understood the predictions. But why reality is this way? No answer. Just the way it is. Let me tell you about Feynman diagrams, because this is where Feynman changed everything. Before Feynman, calculating what happens when particles interact was a nightmare. The equations were impossibly complex. Pages and pages of algebra. Most physicists couldn't do it. Feynman invented a visual method. He drew pictures, simple diagrams showing particles as lines, interactions as vertices. You could look at a Feynman diagram and see what was happening. An electron emits a photon. Two particles collide. A particle decays. Each diagram corresponded to a mathematical term, and you could calculate the probability of an interaction by drawing all the possible diagrams and adding them up. This was revolutionary. Feynman made the impossible possible. Suddenly, physicists could calculate things that were beyond reach before. But here's what's strange. Feynman diagrams show particles interacting in ways that seem impossible. Time running backward, particles traveling into the past, antiparticles, as particles moving the wrong direction through time. And Feynman said, yes, that's what's happening. Not metaphorically, actually. An antiparticle is a particle moving backward in time. Does that make sense? No. But it works. The math works. The predictions work. Feynman's idea was that you shouldn't think about what's really happening. Just calculate what you observe. And if the calculation matches the observation, you're done. Don't ask deeper questions. Except people do ask. People always ask. What's really happening when particles interact? What is an electron doing between measurements? What does it mean for time to run backward? And Feynman's answer was always the same. Those questions don't have answers. Or rather, the questions are wrong. You're asking for a classical picture of a quantum process. And there is no classical picture. Quantum mechanics is the picture. The math is the picture. There's nothing deeper. And this frustrated people. It still frustrates people. Because we want reality to make sense. We want things to be made of stuff. We want cause and effect. We want objects to have properties. But quantum mechanics says no. Objects don't have properties until you measure them. Cause and effect gets blurry at small scales. Things aren't made of stuff. They're made of fields and probabilities and interactions. Feynman spent his whole life working with this, calculating with this, teaching this, and he never pretended to understand it. He was honest, brutally honest. He said, I can tell you how nature behaves. I can give you the rules, but I cannot tell you why. And maybe there is no why. Maybe reality just is. Let me tell you what this means for you, for your life, for the world you think you're living in. Everything around you, everything you see and touch is governed by quantum mechanics. The solidity of matter, electromagnetic repulsion. The stability of atoms, quantum mechanics. The fact that you don't fall through the floor, Pauli exclusion principle. A quantum rule that says two electrons can't be in the same state. Chemistry, quantum mechanics, biology, built on chemistry, built on quantum mechanics. You are a quantum mechanical system. Your thoughts, your memories, your consciousness, all of it runs on neurons firing. And neurons fire because of ion channels, and ion channels work because of quantum mechanics. Does that mean your thoughts are quantum? Maybe, maybe not. We don't know. Feynman didn't know. But the possibility is there. The possibility that consciousness itself is a quantum phenomenon. And if that's true, then you are not just observing quantum weirdness. You are quantum weirdness. Here's something Feynman loved to point out. When you look at something, photons bounce off it and hit your eye. Those photons are quantum mechanical. They exist in superposition until they hit your retina. Then they collapse. They become definite, and your brain interprets the signal, constructs an image, creates the experience of seeing. But what you're seeing isn't the object, it's a reconstruction, a model built by your brain from quantum interactions. You have never seen the real world. You've seen your brain's interpretation of quantum events. Every single thing you've ever experienced is mediated by quantum mechanics. And quantum mechanics says the world doesn't exist in a definite state until it's measured. So what does that mean? Does the world exist when you're not looking? Feynman refused to answer. He said the question is meaningless. The world behaves as if it's there. The predictions work. That's all you get. Asking if it's really there is philosophy, not physics. But people kept asking, and Feynman kept refusing, not because he didn't care, but because he thought the question had no answer, or at least no answer that could be tested. And if you can't test it, it's not science. Now, let me tell you about the path integral formulation. This is Feynman's greatest contribution to physics, and it's the strangest way of thinking about reality ever invented. Here's the idea. When a particle moves from point A to point B, it doesn't take one path, it takes every possible path. Simultaneously, all of them. Every route, no matter how absurd. Straight lines, curved lines, zigzags, loops, paths that go halfway around the universe before arriving at B. All of them at the same time. And each path contributes to the final probability. You add up the contributions from every path. Some paths add constructively, some cancel out. And what you get is the probability that the particle arrives at B. This isn't a metaphor. This is the math. This is how you calculate quantum mechanics. A particle explores every possible route, and the route it seems to take, the one you observe, is just the average of all possible routes weighted by probability. Does that make sense? No. Did Feynman think it made sense? He said, "I don't like it any more than you do. But it works, and it works beautifully." The path integral formulation predicts everything the old quantum mechanics predicted, but it gives you a different way of thinking about it. Instead of particles in definite states collapsing into other states, you have particles exploring all possibilities and reality emerging from the sum. And this raises a terrifying question. If particles take every possible path, does that mean every possibility happens? Does it mean there are versions of reality where the particle took different routes? Feynman didn't say, but others did. The many worlds interpretation, the idea that every quantum event splits reality into multiple branches. Every possible outcome happens, just in different universes. You measure an electron's spin. In one universe, it's up. In another, it's down. Both happen. Both are real. And there are now two versions of you, one in each universe. And this happens constantly. Every quantum interaction. Trillions of times per second. Reality branching endlessly. Does Feynman's math require this? No. Does it allow it? Yes. Is it true? Nobody knows. Can't know. Because you can't observe the other branches. You're stuck in one. So the question becomes untestable. And Feynman hated untestable questions. He said, if it doesn't make a difference to any experiment, it doesn't make a difference. So stop worrying about it. But people do worry, because if many worlds is true, then everything that can happen does happen. Every choice you didn't make, you made in another universe. Every path you didn't take, you took somewhere else. There are versions of you living completely different lives, and you'll never meet them, never know them, never confirm they exist. Is this reality, or is it just math run wild? Feynman would say, doesn't matter. Calculate what you observe. Predict what you measure. That's physics. The rest is storytelling, but the stories haunt us. They change how we see the world. If every possibility is real, then what does it mean to make a choice? What does it mean to say something is true? Feynman didn't answer these questions. He didn't think they were his job. His job was to calculate, to predict, to test. And he did that better than almost anyone in history. But the questions remain. And they're uncomfortable. Reality might be far stranger than we imagine. Far stranger than we can imagine. And Feynman knew this. He embraced it. He said, "The world is not only queerer than we suppose, it's queerer than we can suppose. Our brains aren't built for this. We're not wired to understand superposition or entanglement or path integrals. We're wired to survive on the savannah, to find food, to avoid danger. Quantum mechanics didn't matter to our ancestors, so we didn't evolve intuitions for it. And now we are stuck, trying to understand a reality that defies every instinct we have." Here's what Feynman said about teaching quantum mechanics. He said, "Nobody really understands it, so don't feel bad if you don't understand it. I don't understand it. Your professor doesn't understand it. Nobody does. We just know how to use it. And that's enough." But is it enough? Is it enough to know the rules without knowing why? Feynman thought so. He thought understanding meant being able to predict. If you can predict, you understand. But most people want more. They want meaning. They want a story. They want to know what reality is made of. And Feynman said, reality is made of mathematics. The equations describe everything. There's nothing beneath the equations. The math is the thing itself. Does that satisfy you? Probably not. It didn't satisfy most people. But Feynman didn't care about satisfying people. He cared about truth. And the truth is that reality doesn't owe us an explanation. Reality doesn't owe us comfort. Reality just is. And we're lucky that we can describe it at all. That we can make predictions. That we can test them. That we can build technology based on quantum mechanics, even though we don't truly understand it. Here's something that blew Feynman's mind. The same equations that describe an electron also describe light and sound and vibrations in a crystal. Quantum mechanics is universal. It's not just about tiny particles. It's about everything. The only reason you don't see quantum effects in everyday life is because you're too big. You're made of trillions of particles, and when you have that many particles, the quantum effects average out. The superpositions collapse. The probabilities become certainties. You behave classically, but you're not classical. You're quantum. You're just too big to notice. And that's weird, because it means there's no dividing line. There's no point where quantum mechanics stops and classical mechanics starts. It's all quantum, always. Classical mechanics is just an approximation, a useful fiction. The real world is quantum all the way down and all the way up. Now, Feynman discovered something else that changed everything. He realized that light is made of particles, photons, but photons are also waves. They're both, at the same time. This is called wave-particle duality, and it's not just light. Everything has wave-particle duality. Electrons, protons, atoms, even molecules. Even you. You have a wavelength. It's incredibly small, too small to measure. But it's there. You are a wave. You are also a particle. You are both. How can something be both a wave and a particle? Feynman said, it can't. Not in the way you're thinking. It's neither. It's something else. Something that has properties of waves and properties of particles, depending on how you measure it. But it's not actually either one. It's a quantum object. And quantum objects don't fit into classical categories. This is where language fails. We don't have words for what these things are. We only have words for classical objects, balls, waves, things we experience in everyday life. But electrons aren't balls, and they're not waves. They're electrons. And the only way to describe them accurately is with math. Feynman knew this. He knew that any attempt to visualize quantum mechanics would fail, because visualization is classical, and quantum mechanics is not. So he stopped trying. He just calculated, and he taught others to do the same. But people still want pictures. They want analogies. They want to understand. And Feynman said, you can't. Not really. You can get used to it. You can develop an intuition for the math. But you'll never understand it the way you understand a bouncing ball. Because it's not like a bouncing ball. It's not like anything you've experienced. And that's okay. That's how nature is. Let me tell you what Feynman thought about reality. He thought it was beautiful, incomprehensible, yes. Strange, absolutely, but beautiful. He said, the fact that we can know anything about the universe is a miracle. The fact that the universe follows rules, that those rules are mathematical, that we can discover them. That's astonishing. We're pattern-seeking apes on a tiny planet. And we've figured out the fundamental laws of reality. We've split the atom. We've built quantum computers. We've tested quantum mechanics to absurd precision. And it works every time, without fail. That's beautiful, even if we don't understand why. Maybe especially because we don't understand why. The mystery makes it more beautiful, not less. Feynman loved the mystery. He loved the strangeness. He loved the fact that reality surprised him. He said, if you're not surprised by quantum mechanics, you haven't understood it. And he was surprised his entire life. Every time he calculated something, every time he taught it, every time he thought about it, he found something that amazed him. That didn't make sense. That defied intuition. And he loved it. Here's the hardest part. The part that makes nothing feel real. If particles don't have definite properties until measured, if they exist in superposition, if they take all possible paths, if reality is just probabilities collapsing into actualities when we observe them, then what is real? Is the table in front of you real? It's made of atoms, and atoms are mostly empty space. And the particles in those atoms don't have definite positions. They're clouds of probability. So is the table real? Feynman would say, define real. If real means it behaves consistently. If real means you can measure it. If real means it affects other things. Then yes, the table is real. But if real means it exists independently of observation. If real means it has definite properties, whether you measure them or not, then no. The table is not real in that sense. It's a quantum system, a collection of probabilities, and only when you interact with it does it become definite. Does this mean reality is created by observation? Feynman refused to say. He said, the question is poorly defined. What do you mean by created? What do you mean by observation? These are vague words. Physics deals with precise words, with measurements, with predictions. And the predictions work whether or not you philosophize about what's real. But the question haunts us. Because if reality depends on observation, then what was the universe like before observers existed? Was it all superposition? All probability? Did the Big Bang happen in a definite way? Or did it happen in all possible ways and only become definite when the first conscious being observed it? These questions kept physicists up at night. They still do. And Feynman's answer was always, I don't know. Maybe the questions are wrong. Maybe reality doesn't work the way you think it works. Maybe observation doesn't mean consciousness. Maybe it just means interaction. Any interaction. Particles observing each other, collapsing each other's wave functions. No consciousness required. Or maybe consciousness does matter. Maybe the universe needed observers to become real. Feynman didn't know. Nobody knows? Can't know. Because we can't go back before observers existed and check. So the question remains open forever. Here's what I want you to take away from this. Feynman showed us that reality is not what it seems, not even close. The world is built on rules that make no intuitive sense. Particles in two places at once, measurements changing outcomes, empty space filled with energy, time running backward. All of this is real. All of this has been tested, and it works. But nobody understands why. Not Feynman, not Einstein, not anyone. We can use it. We can predict it. We can build technology with it, but understand it. And maybe that's okay. Maybe understanding isn't the goal. Maybe the goal is just to describe reality as accurately as possible, to make predictions, to test them, to build on what works. And Feynman did that better than almost anyone. He took the weirdness of quantum mechanics and turned it into a tool that explained everything from the behavior of subatomic particles to the workings of stars. And he did it without pretending to understand what it meant. He was honest. He was humble. He said, "I don't know." And that honesty is what made him great. Because the universe doesn't owe us understanding. The universe is under no obligation to make sense. And Feynman accepted that. He embraced it. So what's the lesson here? The lesson is that reality is stranger than you can imagine, that your intuitions are wrong, that the solid world you think you live in is an illusion. Not a malicious illusion, just an approximation, a useful model your brain constructs to help you survive. But it's not the truth. The truth is quantum. The truth is probabilistic. The truth is that nothing is certain until it's measured. And even then, it's only certain in that moment. Everything is constantly shifting, constantly changing, constantly existing in multiple states until forced to choose. And you're part of that. You're not separate from the quantum world. You are the quantum world, made of the same particles, following the same rules, just too big to see the weirdness directly, but it's there, always, underlying everything. And once you know this, nothing feels quite real anymore. Because what does real even mean? Feynman asked that question his whole life, and he never found an answer he was satisfied with. Maybe there is no answer. Maybe real is just a word we use to describe our experiences. And experiences are quantum interactions, probabilities collapsing, wave functions falling into definite states. That's all reality is. That's all it's ever been. And somehow, impossibly, we figured that out. We tiny creatures. We quantum systems that can think about quantum systems. We discovered the rules. We wrote them down. We tested them. And they work. That's the miracle. Not that reality makes sense, but that we can describe it at all. That we can navigate the strangeness and find patterns, find laws, find truth, even when that truth is incomprehensible, even when it violates everything we thought we knew. That's what Feynman taught us. Don't expect the universe to be simple. Don't expect it to make sense. Just calculate, just predict, just test, and marvel at the fact that it works at all. That's the beauty. That's the wonder. That's reality. Strange, beautiful, incomprehensible reality. And nothing will ever feel quite real again.